Shandong Shuangbai City Regional Coordination Dynamic Signal Control Optimization System. Hello leaders present. We are Shandong Shuangbai Electronics Company, Limited. Our company is mainly engaged in the research and development and sales of intelligent traffic signal products. The specific business content mainly includes 4 major systems and 3 major products. The 4 major systems are the Big Data Traffic Signal Control Platform, namely the Super Signal Control System, Regional Coordination Signal Optimization System, Traffic Flow and Green Loss Collection System, and Traffic Event Monitoring System. These 4 systems can be purchased separately for independent operation and use, or can be purchased together for shared database comprehensive use. Our 3 main products are Big Data Traffic Signal Machines, Video Vehicle Detectors, and Leishi Integrated Machines. Some of the products have reached the leading level in China. Today, we will focus on introducing the Urban Regional Coordination Dynamic Signal Control Optimization System, abbreviated as the Regional Coordination Signal Optimization System, to all leaders. The main function of this system is to analyze the traffic flow at each intersection and on the road, as well as the green loss time at each intersection, generate a reasonable timing plan and send it to the traffic signal, in order to enable vehicles traveling on each road in the urban area to pass in a bidirectional green wave. This system is developed using cutting-edge core technologies such as advanced 3-dimensional traffic coordinates, green wave phase locking, time misalignment of vehicles passing through intersections, and spatial misalignment of vehicles passing through intersections. Our company's Regional Coordination Signal Dynamic Optimization System has reached the leading level in China, that is, the first level in China, and has passed the appraisal of national scientific and technological achievements. This system models various intersections on urban roads to achieve a green light start and green light passage for vehicles, allowing each road in the urban area to achieve bidirectional green wave passage, that is, east-west road bidirectional green wave passage and north-south road green wave passage. Implement a 4-way green wave zone at road intersections. At the same time, this system can also combine the traffic flow and green loss data at various intersections to achieve dynamic green wave zones. This system fundamentally solves the problem that some manufacturers can only adjust parallel roads when debugging green wave belts. Once the roads intersect, it is impossible to achieve green wave traffic, that is, it fails to coordinate the intersection points of each green wave belt road, and therefore cannot achieve true regional coordination. At present, there are many manufacturers on the market that do green wave belt tuning, and some manufacturers use individual adjustments at each intersection, resulting in poor linkage. Alternatively, only a few intersections can be done, and increasing the number of intersections makes it difficult to achieve green wave optimization, resulting in high tuning costs and unsatisfactory results. Alternatively, only parallel road sections can be optimized, and cannot solve the optimization of intersection road sections. The Regional Optimization System of Shandong Shuangbai can dynamically optimize from road sections to sub-areas, and then to regions, ultimately achieving green wave traffic throughout the entire region and maximizing traffic efficiency at each intersection. Now let's take a look at our tuning system. We will introduce this system from 7 main aspects. First, modeling of intersections within urban areas. 2. Basic data research. 3. Regional signal optimization calculation. 4. Verification of the plan. 5. Distribute the plan and generate a timing file. 6. Plan road testing and data collection. 7. Save timing files. Firstly, let's take a look at the functionality of the first module, which is the intersection modeling function in urban areas. Taking the 5 intersections of Mount Taishan Avenue as an example, we will mark and file the intersections to be optimized on the GIS map in turn. based on the current actual operating phase input into this system. Let's have a look. This is the file of each intersection that we have established. The scheme configuration of the intersection between Mount Taishan Avenue and the affiliated hospital. This is the scheme configuration of the intersection of Mount Taishan Avenue and Jiayuan Road. This is the scheme configuration of the intersection of Mount Taishan Avenue and Wangye West Road. This is the scheme configuration of the intersection of Mount Taishan Avenue and Wangye East Road. This is the scheme configuration of the intersection of Mount Taishan Street and Newspaper Building. After marking the 5 intersections, the system automatically calculates the distance between each intersection. Let's take a look at the second part of the system's functions, basic data research. Research the current green loss data of each phase at each intersection, rationalize the release time, cycle, and driving speed. We collect the green loss data of each phase at each intersection through a green loss collection system, or control the green loss of each phase within a reasonable range through on-site observation and other methods, while determining the unified green wave cycle of the entire road. Determine the actual driving speed of the road through our road testing terminal. We will continue to look at the third part of the system's function, regional signal optimization calculation. Generate reasonable timing schemes and phase differences. This system comes with multiple optimization strategies for users to choose from, including priority-based calculation, region-by-region calculation, green wave optimization strategy, and automatic green wave optimization strategy. We can choose and use them according to actual needs. This part of the function is the core of this system, and the core is the algorithm, with each strategy corresponding to a different algorithm. After selecting the corresponding strategy to automatically generate the solution, we can also manually adjust it. Adjust the phase difference by dragging the green pillars at each intersection up and down to achieve bidirectional coordinated green wave traffic. At this point, we import the simulation trajectory. This trajectory is generated based on our measured driving speed, observing whether it happens to pass through each intersection at the green light state. We can observe whether the setting is reasonable and feasible by moving the trajectory up and down. At the same time, this system can also interface with the green loss collection system to achieve dynamic adjustment and distribution of solutions. The green loss collection system can be achieved by analyzing the auxiliary code stream of existing electronic police cameras. This is our green loss collection system. The video vehicle detector uses the existing electric alarm equipment at the intersection as the collection terminal to collect the traffic volume covered by the monitoring camera. Through the real-time data collected, it provides data support for the optimization system of the traffic area and the adaptive control and induction control of the signal. It can also make statistics on information such as vehicle speed, queue length, lane occupancy, and phase green loss. Easy installation, no need to rewire for construction, just borrow the resources of intersection police and checkpoints. No relay equipment required. Local data storage, upload independent of signal machine, and can be installed independently. The detection rate is as high as 99.3%. Tested by the Traffic Safety Product Quality Supervision and Testing Center of the Ministry of Public Security. It can connect with other brands of signal machines and monitoring camera equipment in the industry. Flow chart. Within the control platform, video images can be synchronously viewed. Summary data report of vehicle flow statistics. Utilize existing electronic police cameras and checkpoint camera substreams for secondary data analysis and processing. Realize the collection of traffic flow without the need for repeated investment and construction. The fourth part is the verification of scheme rationalization. We find the driving trajectory in the time-distance graph interface. Click with the mouse to check whether the actual driving speed in the blue actual driving trajectory matches the setting. We observe whether there is periodic interruption in the time-distance graph, whether it passes through underpasses, elevated roads, etc., and adjust the coordination phase according to actual needs. For example, for underpasses, elevated roads, etc. At intersections, we can incorporate left turn signals into green wave coordination. This is our regional coordinated road testing equipment, which can collect the driving speed, coordinates, driving videos, etc. of the green wave belt. This is our green band calibrator, which can verify whether the green band effect is accurate and whether it operates according to the set plan. It can be installed on a mobile phone or computer to verify the accuracy of the operation plan at each intersection on site. The fifth part is to distribute the plan and generate a time allocation file. The time allocation plan optimized through regional coordination can be automatically distributed to traffic signals. Able to automatically issue signals from various brands based on protocols. The sixth part is the solution road testing and data collection. After the optimization system is issued with the plan, we need to verify whether it meets the actual traffic conditions by collecting data from the road test terminal. For whether the optimized timing plan can truly achieve all green wave traffic, we have also equipped a 4-in-1 verification system to verify whether the regional coordination green wave meets the actual situation through real and immutable data. Now let's show you the video of Mount Taishan Avenue after our system optimization. Please watch the video. The upper left part of the screen shows the actual driving trajectory of our vehicle on the GIS map, which can record the actual physical position of the vehicle during driving. The lower part is the time-distance graph generated by our system in the scheme. The green bar in the graph represents the green light time on the green belt road. The lower part of each green bar represents the start time of the green light, and the upper part represents the end time of the green light. The blue smooth curve represents the actual driving trajectory of our vehicle. As long as our blue driving trajectory passes through the green bar, it represents that the vehicle passes through the intersection in a green light state. In practice, the blue driving trajectory is the data automatically collected by our vehicle during actual driving, and there is no possibility of manual falsification. Please watch the video on the right side of the screen. This is a video footage recorded by our road test terminal vehicle during actual driving, which includes our actual driving time, speed, and images of passing through various intersections. At the bottom right is our optimization data, which clearly shows our optimized parking times, whether to stop at each intersection, driving time, and so on. The seventh part is the preservation of timing files. The optimization system can save the optimization of the entire urban area as a file, which can be opened for further optimization or retrieval in the future. Configuration schemes can also be exported and archived in a spreadsheet format. Our company corrects and explains the following erroneous views that some personnel may be misled by the propaganda of other units. First, on the green wave road, there is always a red light after encountering a red light, that is, the red wave zone. Second, it is impossible to achieve a bidirectional green wave band. Third, it is impossible to achieve a four-way green wave zone, that is, a crisscross green wave zone cannot be achieved. Fourth, without automatic flow collection data, it is impossible to achieve a green wave band. In response to the first scenario of encountering a red light on a green wave road, and remaining at a red light, known as the red wave zone, let's take a look at the green wave time interval chart. We start at the green light at the first intersection and drive down to the next intersection, starting at the bottom of the green bar. If we stop and wait until the next green light time starts due to other reasons, we started driving again according to the setting of the green wave band, starting from the lower end of the green column. That is to say, if we miss this green wave band, we can drive on the next green wave band and achieve all the green lights. For the second scenario where it is impossible to achieve a bidirectional green wave zone, we first click on the time distance map button, and the 8 green wave road time distance maps are displayed in front of us. Now we zoom in to view the time distance map of Okma Road. Okay, for all intersections with Okma Road, we start from the green light at the first intersection and continue to the right, that is, driving in a forward direction, until the last intersection of our green wave zone. The driving trajectory of the vehicle passes through the traffic light intersection in the green light state. We start from the green light at the last intersection and continue to the left, that is, drive in the opposite direction until the last intersection on our green belt, where the vehicle's trajectory passes through the traffic light at the green light state. That is to say, whether it is forward or reverse traffic, it passes under the green light signal state, which is what we call a bidirectional green wave. In response to the third situation where it is impossible to achieve a four-way green wave zone, that is, a crisscross green wave zone cannot be achieved, we looked at the coordinated road network map of this area on a GIS map. This green wave road network map is a real success case. On the map, we saw both east-west green wave roads and north-south green wave roads. We take Renmin Road and Xingyang Road as examples to analyze. We first click on the time distance map button, and the time distance map of the 9 green wave roads is displayed in front of us. Now, let's zoom in and view the time distance map of Xingyang Road. Okay, we can see that the blue driving trajectory displays bidirectional green wave traffic, whether viewed from left to right or right to left. We need to pay special attention to Xingyang Road and Renmin Road. When vehicles pass through this intersection, they are bidirectional green wave traffic in the north-south direction. Let's take a look at the coordination direction interface. Xingyang Road coordinates the north-south direction. Let's zoom in and take a look at the time distance map of Renmin Road again. Okay, we can see that whether viewed from left to right or right to left, the blue driving trajectory shows two-way green wave traffic. We need to pay special attention to Xingyang Road and Renmin Road. When vehicles pass through this intersection, it is two-way green wave traffic in the east-west direction. Let's take a look at the coordination direction interface, and Renmin Road coordinates the east-west direction. By looking at these two time interval maps, it is possible to achieve a green wave zone in 4 directions at an intersection, as the north-south passage passes through Renmin Road and Xingyang Road in a bidirectional green wave passage, while the east-west passage passes through Renmin Road and Xingyang Road in a bidirectional green wave passage. This is calculated by us through cutting-edge core technologies such as advanced 3-dimensional transportation coordinates, green wave phase locking, and vehicle spatial misalignment, which has certain scientific principles. In response to the fourth situation where without automatic traffic collection data, it is impossible to achieve a green wave band, we need to first take a look at the 4 major elements of the green wave band, rationalized same or multiple cycles, clock consistency, consistent time periods, and rationalized phase difference. Compared to the green wave theory, the flow mainly determines whether the release time of each phase is reasonable and whether green loss phenomenon will occur, thereby determining the reasonable release cycle. If there is no flow detector, we can also determine the release cycle and reasonable release time for each phase through manual observation or long-term statistical methods. Therefore, it can be said that without automatic flow collection data, a green wave band can also be achieved. This system also has many other functions, such as real-time optimization, green loss statistical analysis, multi-period scheme setting, dual-cycle green wave, non-identical dual-cycle green wave, asymmetric signal release green wave, overlapping green wave, asymmetric vehicle flow green wave, asymmetric vehicle speed green wave, red waveband setting, unidirectional green waveband setting, and many other highlights will not be further elaborated here. In the later stage, we can learn more about optimization knowledge through practical operation of this optimization system. Through the above display and introduction, we summarize as follows. First, this system achieves regional coordination of the green wave zone and the coordination of intersections of multiple main roads, that is, each road in the east, west, north, and south can achieve a bidirectional green wave zone. Second, be able to adjust the dynamic green wave band by combining the green loss data of each intersection. Third, having the ability to collect real driving data and verify whether the setting of the green wave zone is reasonable and feasible. Fourth, able to connect with traffic signals from multiple brands and achieve automatic distribution of solutions. Fifth, able to generate regional dynamic coordination schemes based on green loss data, achieving regional coordination control. Sixth, to improve optimization efficiency, the road test terminal usually generates a reasonable green wave band timing scheme by collecting twice. Seventh, it has saved a lot of manpower and material costs, improved optimization efficiency and accuracy, and broken the bottleneck phenomenon of only being able to set parallel green wave bands. Eighth, the Urban Regional Coordination Dynamic Signal Control Optimization System is at a leading level in China and has obtained relevant scientific and technological achievements appraisal reports.